Okay, welcome to part 5 of problem 3. Here we need to calculate the system's total energy, and it gives us a little hint here that total energy is equal to the spring potential energy plus the rotational kinetic energy. Okay, so let's go ahead and start by writing that out here. The total energy of the system is equal to the potential energy of the spring plus the rotational kinetic energy. We'll note that with a little r there. Okay, and then we can go ahead and start plugging in our known equations for these. So the known equation for a potential energy of a spring is 1/2 k, which is the spring constant, and typically it would be times x squared, or the distance squared. But in this case, we have a torsion spring, so it's oscillating on an angle. So we're going to do theta squared. And then that will be plus the rotational kinetic energy. So it's 1/2 I for inertia times uppercase omega squared. In this case, we're using uppercase omega to represent the rotational velocity. Typically, you're probably used to this lowercase symbol, lowercase omega, representing angular velocity, but we're using this to represent the angular frequency. We can't have two variables or two measurements representing one variable representing two forms of measurement. So that's why we have to split it up here. So we have uppercase omega representing the angular velocity. So now that we have these equations, we can start inputting the values. So if you actually remember from the past problem, it gave us theta at time 0 and the angular velocity at time 0. And we can use those values because at any point in time, because it's a simple harmonic system, the total energy will always be the same. The potential energy and the kinetic energy are just going to swap values. So at the beginning, when we pull the spring back and it's at rest, it has a very high potential energy. And then as soon as it moves, it has a very high kinetic energy, and the potential energy lowers. And then it oscillates back and forth, and it goes back to the resting point, and you have a very high potential energy, low kinetic energy, and then it goes back to the high kinetic energy, low potential energy. But the values for the total energy will always be the same. And we can test that here in a second. So let's go ahead and write down our known values. So we know that theta at time 0 was equal to 0.0872, and we know that the angular velocity at time 0 was equal to 2.74. We know that the spring constant K is equal to 0.650. And we have the equation for inertia, which is equal to 1/12 times the mass times the length squared. And we have mass and length. So mass was equal to 0.100, and the length was equal to 0.140. Okay. So we're going to actually test to make sure we're doing this right. At rest, the potential energy should be the highest and the kinetic energy should be the lowest. So first, let's go ahead and find our inertia value, which we actually found a couple problems ago, but we're basically going to plug the mass in and the length in, and sum that up. So that will give us 4 zeros. 4/9. It's going to give us this fraction here. And then if we plug in our initial angular velocity in here, and then we plug in our inertia, and then we plug in our theta and our spring constant. We're going to get these values here. So the potential energy of the system with the spring at time 0 is going to be roughly equal to 2.47, and we'll use scientific notation here, 10 to the power of -3, and our kinetic rotational energy is going to be roughly equal to 0.61 to the power of -3. So as you can see, our potential energy is much higher than our kinetic energy, which proves that these equations are working as intended. So let's go ahead and find the total energy like it asks for. So we're just going to plug in all these values here. So we're going to have total energy is equal to 1/2 K, the spring constant, 0.650, times, it'll be theta squared, so 0.0872 squared plus 1/2 the inertia value, which is going to be that very large fraction there. 1, 2, 3, 4, 5. That's 5 zeros. 49 times our angular velocity there, which is going to be 2.74. My paper's sliding here a little bit. It's going to be squared. Okay. So let's go ahead and input these on our calculator. Find out what we get. So that's going to be 1/2 times the spring constant, 0.650, times our angle, 0.0872 squared, plus 1/2 times our inertia, which is 49, 1, 2, 3, 4, 5, times 2.74 squared. Okay, and that will give us our total energy. So that's going to be total energy is equal to 3.084368667 times 10 to the -3. And that is our total energy for the system. And that will be the end of problem 3. So if you stick around, I'll see you for problem 4.